So far, the compounds we've been working with have looked like this: simple, familiar, and made of only two elements. We call these binary compounds, but the most common chemical compounds in our daily lives aren't really this simple. Instead, they tend to look like this, and these. These new particles are not elements, and you won't find them on the periodic table. Instead, they're made of two or more elements, and they travel as a stable, chemically bonded group of atoms, sharing a charge and reacting to other substances together. These are called polyatomic ions. Let's break down that name and figure out exactly what these new particles are and how they work. If we look at the roots in the term polyatomic ion, we find some important information. First, poly is a prefix that means multiple or many. Then the root atomic tells us that we're talking about atoms here. So these particles are made of several atoms stuck together. Then the last part of the term is the word ion. Ions are particles that have an imbalance of protons and electrons, so they end up with a charge. All of the elements we've worked with so far at some point take on a charge, and we're used to working with these. But these charges are actually shared by the whole group. So even though there are several different atoms bonded together, they all share the same charge as a whole particle. So, to summarize what a polyatomic ion is and why it's important, polyatomic ions are stable groups of atoms that bond together and share a charge. Polyatomic ions are a single particle, just like atoms of the elements we've been working with already. But these atoms are stuck together and they act like a family. It's our job when we're naming compounds and writing chemical formulas for substances that include a polyatomic ion to make sure we protect that family. See the little babies? We want to keep them safe. Take care of the family. Don't hurt the babies. Here's a list of polyatomic ions that we might come across this semester. And these are the most common polyatomic ions that we'll be using. We will use them often, so make sure you're familiar with these. These names and symbols are very important, and you'll have to recognize the difference between these polyatomic ions and the individual elements on the periodic table. So these are the kind of substances we need to learn to deal with. For the most part, polyatomic ions behave the exact same way non-metal elements. They basically act like the red elements. But here's three important rules to remember a few special things about these particles. First of all, polyatomic ions always stay together. Remember, they act like a family? We want to keep that family together, safe and happy, so don't break up the family. Instead, keep the family together, including all of the elements and their subscripts. Second, we need to know that the polyatomic ions never change their names. We're used to changing the names in chemical compounds so that they end with "ide," but we don't do that with polyatomic ions. The only way we can tell the difference sometimes between a polyatomic ion and the simple individual elements on the periodic table is by looking at the name. So we leave the polyatomic ions' names just like they are. We never change them. So, for example, carbonate, that's CO3 with a charge of -2, will never be carbonide. It will always be carbonate. We don't change its name. Nitrate, NO3 with a -1 charge, will always be nitrate. And sulfate will always be sulfate. We don't change the names of the polyatomic ions when we name the compounds they are in. Now, most of the polyatomic ions have names ending with 8. That's a great way to distinguish between polyatomic ions and the individual elements they might sound like. Look out for those 8 endings. They're a great clue that a polyatomic ion is involved. But notice that the names of a few of the elements on the right side of this list don't end with 8. Some of them actually end in "ide," like hydroxide. Hydroxide is very common and we will use it often. It's OH with a -1 charge. It shows up in all sorts of compounds, but the "ide" ending makes it easy to miss. The more familiar you are with this list of common polyatomic ions, the easier noticing them and naming their compounds correctly will be for you. So our second rule is that we never change the name of a polyatomic ion in order to recognize the difference between ions and individual elements. The last thing to remember is that polyatomic ions act the exact same as red elements. Even though they are different than the individual elements they are made of, they behave the same way. That's why they're so common. They are stable and easy to get along with, so they show up in common chemical substances all the time. That means we can use the same rules we already know for naming chemical compounds and writing their formulas. We just have to substitute the polyatomic ions for the individual red elements we've already been working with. Now, there is one exception to this rule. On our list of polyatomic ions, ammonium, NH4, with a charge of +1, is the only ion with a positive charge. Since red elements always have to have negative charges, ammonium instead acts like a blue element. That means we act like ammonium is a representative metal, like the other elements like hydrogen, sodium, and calcium. These are very common in chemical compounds, so we just have to remember this simple exception. While all of the other polyatomic ions we will work with behave like the red elements, ammonium will always behave blue. So, for the most part, trust this rule. All polyatomic ions act like red elements. So we can use the same rules we've already been learning and practicing. Just watch out for that one exception, ammonium. Let's try to put all of these rules into action. Here are a few examples to watch. Let's start with LiOH. Okay, here's a little tip. You can always know that a polyatomic ion is involved when you see more than 2 capital letters in the formula. Here, you can see how the L, the O, and the H are all capitalized. That means there are 3 different elements in this formula. The only time we have more than 2 elements in a single substance is when a polyatomic ion is involved, so start looking out. We need to start this example by figuring out which set of rules to follow, Category 1, Category 2, or Category 3. Well, Li is the symbol for lithium, which is a blue element, and O and H stand for oxygen and hydrogen, but you won't find them together on the periodic table. That's because this is a polyatomic ion. If we go check our polyatomic ion list, we will find that OH with a -1 charge is hydroxide. See, I told you it would show up. So now we know for sure that we're working with a polyatomic ion, and we know that all polyatomic ions act red. So this must be a blue and red compound. That means category 1. So we need our category 1 rules for naming chemical compounds. First, we write the names of both parts of the formula. The metal is lithium and the polyatomic ion is hydroxide. Next, we need to change the ending to I. But wait. Remember rule number 2, never change a polyatomic ion's name. So we leave hydroxide just like it is. Well, that was simple enough. The final name of this chemical compound is lithium hydroxide. Let's try another example of naming chemical compounds including polyatomic ions. Here's CuSO4. Use the trick I showed you. There are 3 capital letters, so we know there's a polyatomic ion in here somewhere. Well, Cu is the symbol for copper, which is a green element. On our polyatomic ion list, we find that SO4 is sulfate. It has a -2 charge and is a very common polyatomic ion. Since all the polyatomic ions act red, we know we're dealing with a category 2 compound. So we need to use the rules we already know for naming category 2 compounds. Step 1 tells us to write the names. That's copper and sulfate. Step 2 says to change the name, but we know not to do that for sulfate because it's a polyatomic ion. Since copper is a green element, it needs a Roman numeral. So step 3 tells us to use the original subscripts and charges to determine copper's charge and the Roman numeral we need for the name. So we break out our AX plus BY equation, and we know that we need to find X. That's the part that stands for copper's charge. Well, our polyatomic ion list showed us that sulfate has a charge of -2, so we can take that back to the equation and plug it in for Y. Now we need to get the subscripts for A and B. Well, in our formula, we can see that copper has a subscript of 1, but there's a problem with sulfate. Remember, sulfate, like all polyatomic ions, is like a family, and we can't break apart the family. So that 4 next to sulfate doesn't mean that there are 4 sulfates. It means that in the one sulfate in this compound, there are 4 oxygen atoms. A good way to visualize this is to put parentheses around the sulfate ion in the formula. Everything inside those parentheses has to stay the same. That's how we protect the family. The 4 is a part of the family, so it can't be changed or messed with. It's not the subscript for the whole sulfate, it's just the subscript for the oxygens that are a part of the sulfate family. The real subscript on the sulfate would be outside of the parentheses. It would be an understood 1. This means there is only one sulfate ion as a part of this chemical compound. That means the value of B here is 1, because there's only one sulfate family. Now that we've filled in what we already know, we can go ahead and solve for x. This equation tells us that x is equal to 2. That means the charge on copper here is positive 2. So we put the Roman numeral 2 in between copper and sulfate. So our final chemical name here is copper 2 sulfate. That's a tough one. If you need to go back through the last part of the video just to make sure you've got it, now is the time. Ask your teacher if you still have questions about naming with polyatomic ions. But sometimes we need to write the formula for these kinds of compounds instead of writing their name. Here are 2 examples where we know the name, we just need to write the formula. Here's barium carbonate. Barium is a blue element, and its symbol is Ba. The 8 ending on carbonate should give away that it's a polyatomic ion. We can check our polyatomic ion list just to make sure, and there's carbonate, CO3 with a -2 charge. Polyatomic ions act like red elements, so we know we need to use the category 1 rules for writing chemical formulas. We start by writing the symbols for our 2 particles, Ba for barium and CO3 for carbonate. Don't forget, that 3 is not a subscript for the whole carbonate ion, it's a part of the family. 1 carbon atom and 3 oxygen atoms. Be careful with those subscripts. We have to take care of the family. Now we need to check out the charges and see if they equal out. If they don't, we need some subscripts. The periodic table tells us that barium always has a charge of +2, and the polyatomic ion list told us that carbonate always has a charge of -2. +2 and -2 equal out automatically, so we don't need to add any subscripts. We put a Ba and a CO3 next to each other, and BaCO3 is our final formula. Here's a little tougher example, copper 2 phosphate. We've seen a lot of copper compounds, so we know that copper is a green element, and the 8 ending on phosphate gives away that we're dealing with a polyatomic ion. The polyatomic ion list confirms it, and we know that we're working with a green and red compound, so we need category 2 rules for writing formulas. Step 1 gives us Cu for copper and PO4 for phosphate. That comes straight from the polyatomic ion list. Now we need the charges. The name tells us this is copper 2, which means copper with a +2 charge. The polyatomic ion list tells us that phosphate has a charge of -3. If we use our AX plus BY equation, we can plug in that information and find an LCM, and then we can solve for our A and B subscripts. We know copper's charge is +2, and we know phosphate's charge is -3. The LCM of 2 and 3 is 6, which means we need A times +2 to equal +6, and B times -2 to equal -6. That means A must be 3 and B must be 2. So our subscript for copper is 3, and our subscript for phosphate is 2. Let's look at those parentheses I've written around PO4. Remember that polyatomic ions are families. That means the 4 has to stay as a part of the family. It can't be changed. Instead, we put parentheses around PO4 to keep it safe and put the subscript outside. This tells us there are 2 phosphate families in this chemical compound. So our final correct chemical formula is Cu3 parentheses PO4 close parentheses 2. Cu3PO4 2. This example is about as complicated as it gets, so a little practice should clear up any questions you still have. That's how we work with polyatomic ions. For the most part, we can follow the exact same rules we've already been learning and practicing. We just have to learn to be careful of a few details. Remember, we keep the polyatomic ion families safe with parentheses, we never change their names, and we treat them just like individual red elements that we've already been working with. Here are 3 examples of compounds that include a polyatomic ion. For the first and third examples, you should write the formulas, and for the second example, you should write the name. Pause the video and take your time practicing this important skill. Here are the answers. I'll go over each of these next. For the first example, we have the name calcium chlorate. Chlorates are very common in chemistry, so it's worth getting familiar with this polyatomic ion. First of all, we know that calcium has a positive 2 charge, and the polyatomic ion list tells us that chlorate has a negative 1 charge. Those do not automatically equal out, so we need to use AX plus BY. The LCM of 2 and 1 is 2, which leads us to our A and B values of 1 and 2. That means calcium gets a subscript of 1, and carbonate needs a subscript of 2. Be careful to protect the family here. Put parentheses around chlorate and put the subscript outside. So your final answer should be CaClO3, 2. The second example gives us the formula FeC2H3O2 3. Wow, that's a lot of letters. The parentheses here are the giveaway that this is a polyatomic ion. According to the polyatomic ion list, C2H3O2 is acetate. That gives us the basic name of iron acetate, but iron is a green element, so it needs a Roman numeral. We can use AX plus BY to find the charge on iron. We already know that acetate has a charge of negative 1, that's from the polyatomic ion list, and we can see in the original formula that iron has a subscript of 1 and acetate has a subscript of 3 from outside the parentheses. We solve for X, and we find X equal to 3. That means the charge on iron is positive 3. So we add a Roman numeral 3 to the middle of the name, iron 3 acetate. The last example is ammonium sulfide. Ammonium is that tricky polyatomic ion that acts blue, even though all of the others act red. Watch out though, you might be so focused on polyatomic ions that you miss sulfide. The "ide" ending means that it's just the element sulfur, not a polyatomic ion. Now this trick doesn't always work, but it's a good start. You can always check again on the polyatomic ion list. The polyatomic ion list tells us that ammonium is NH4 with a positive 1 charge, and the periodic table tells us that sulfur has a charge of negative 2. So we plug these into AX plus BY, and we find the LCM of 1 and 2 is 2. So that means A must be equal to 2, and B must be equal to 1. So NH4 needs a subscript of 2, and S needs a subscript of 1. Don't forget the parentheses around ammonium. You have to protect the family. So our final formula here for ammonium sulfide is NH4 2S.